All right, welcome back to Chapter 12, Three-Phase Circuits. This is Part 2. In Part 1, we introduced three-phase circuits, the idea of balanced circuits, and we went through to the YY configuration of a circuit, a source, and a load. Today we're going to begin in 12.4 with the balanced Y-delta connection. Remember, balanced means all elements of the type are the same. So in a load, that means all the elements are in fact equal. In a source, that means the amplitudes of the elements are the same and the phase shift is uniform around the circle. So for three-phase, that means 100 to 120 degrees phase shifts. In the Y connection, recall, it's three sources, 120 degrees apart, with an amplitude. Here are the three indicated in the picture. If we attach a load, and the load now is a delta load as opposed to a Y load, we see there are three currents, IA, B, and C, on the lines. There will be phase currents down here that will be made up of the current through an individual load, and that current is a function of the voltage across the load, which will be the line voltage, and it of course is made up of a combination of the phasor combination of the appropriate phase voltages. You may recall for the phase voltages we had VAN, and we needed to find VAB, right? We needed to take VAN minus VBN. So in other words, it was VAN plus VNB. All right, so we had that. And so we had VAN. VBN was down here, right, in a positive sequence. VBN was down here. So the negative form of it was up here. And when we put the two together, we got this with our 30 degrees, right? You'll remember that. We got that. You can do the same thing with all the other combinations, and you get, again, the 120 degree offset once you find the first one that's going on. Okay, so the four elements we want to find, here we have two of them, the phase voltage and the line voltage. Now we want phase current. Whoops, I wrote over it a little bit there. We want the phase current, that's the IAB. And those are easily determined now from the AB, the VAB that we got. Capital VAB subscript and small VAB right now are the same thing. Important to keep that straight in the pictures. I notice in this text the author freely switches, it seems to me, between small letters, lowercase, and uppercase, and wise to just always look at the pictures being referenced so that you don't make an assumption that isn't going to be true. The other two currents then are these. So now of the four items that we need to analyze three-phase circuits, line and phase, voltage and current, we easily have three of them in this balanced Y-delta configuration. So now we just have to find the line current, and it is, as the equation shows, the simple difference. It's a nodal equation here. Keep doing that. This is a nodal equation right here in that upper node where the AB is the one entering and CA is the one exiting. So I've drawn here in the right the first picture. Here's our IAB if it were oriented at 0 degrees, right? And we don't know this because remember IAB is actually going to be a function of the angle of Z. But for now we can everything is going to be relative around the circle. So we can start with IAB being positive on the 0 axis. ICA in a positive sequence, ABC sequence, is going to be up here. This is where VCA is. And so this is ICA. Now what we want to do is subtract it from there. And so this is another way of indicating it. If I were to take ICA, I could call it IAB at minus 120 and minus 240 degrees. Be another way of delineating ICA. So here that is written. And here I am making that vector of minus ICA. Okay, so what are we going to do? If I'm going to subtract ICA, if I'm going to subtract this one, it's the same as adding this one, right? So that's going to be our usual thing out here. So this should be A, right? And we know, because we've done it a zillion times at this point, this is going to be 30 degrees. And this is going to be what? Our square root of 3 times IAB, the magnitude of it. Okay? If we break that down, we can see here's the negative part in the picture. This is 1/2. You'll get familiar with these numbers, right? This is 0.866 over here. This is 1/2. Right, and this is that standard 30, 60, 90 triangle. This is 1, 2, the square root of 3. So this could easily be 1/2, 1, and 1/2 of the square root of 3. And that's where these numbers come from all the time. Okay, you're going to be seeing those over and over again. So finally, there it is in picture form as well as in the equation form. We have the line current. So that's the fourth of the elements. And for any line current, the magnitude is going to be square root of 3 times the phase current. The line current is always bigger than the phase current. Similarly, we saw the line voltage is bigger by the square root of 3 from the phase voltage. Okay, here's the picture, all three of them. Nice and pretty and clean. But it's the same math repeated all around. The nice thing about the three-phase is generally you do the math in one place and then you can impute it at 120-degree pieces as you go around. Another thing to notice or to remember, if I have, like I do here, I have the, I don't know why that keeps coming up, but I'm given the delta impedance. The Y impedance is 1/3 of that, right? And that was derived back in chapter 9, I believe. We derived that. We used this before already. So, so there's that. And when you do that, then we have this really nice single loop circuit which contains the phase voltage that we were given, could easily get, the line current that we want. We got to stop doing that. The line current that we want, and now a load that is related to the delta load, but it's one we can manage. And this we like. You can easily visualize the single loop nodal equations here. All right, I want to take a look. It's all printed out here. I just copied this out of the text, and you can go through it at your own pace. But I wanted to take a quick look at example 12.3 because it shows two methods of dealing with the problem. The first is maybe the more laborious it looks like, but the more analytical one. And the second just uses the single phase analysis. So let's look here. Mostly at the first one. We've got our Z is given and a phase voltage. So they've conveniently converted this to a phasor form. Kind of nice. We can estimate it's a 1, 2, whatever, a square root of 5 triangle, something like that. But at any rate, we know it's something probably a little less than 30 degrees and something bigger than 8, but not a lot. So that's what we have. The phase voltage is available there. I got to find an easy way to get rid of this without having to go through this all the time. All right, so we have the phase voltage was given. That's 100. And we know we can easily get to the, because we just derived all this stuff, we can easily get to the phase voltage. Now, phase currents, you see here, this is simply saying, remember this side of the picture where we had this, and here's our innocent-looking IA coming in here. Here was IAB, and here is, this way, ICA. So we're going to want this to be equal to IAB minus ICA, right? But we know these two are very easily the line voltage, which we now have, 173.2 at 40. Whoops. And we're going to divide it by Z, which is our 8.944, right, at an angle of 2657, right? Finds each of those currents. There's a similar one here. You can look at it in the text. It's this guy, right, that. And we now have this, right? And all we need to do is subtract the two, right? We know that IAB minus ICA is going to be this. So it's we also went through, those are phase currents that have been found. We're asking for both phase and line currents. After that, we went through that nice calculation that showed, and I want to take this apart because look, here is that simple statement. It's IAB, and he doesn't do this often in the text, times the square root of 3. We like that. That's the magnitude increase at an angle of minus 30, right? That was a fact. But now what we need to look at in this case is our IAB is not at 0 degrees. So we have to be careful about this guy. This is not at 0 degrees. So in that case, this is going to be a multiplier of the amplitude. That's fine. This is now going to take the place of what? An offset. We're not used to doing that. We're used to having everything start at 0. So these offsets, we don't think of them as offsets. We think of them as a new angle. So we can take square root of 3 times IAB. So that's square root of 3 times, or whatever it was up there, 19.36. That was a magnitude. Okay, we got that. Now the angle is, what is it? It's our 13.43, and we're offsetting it 30 degrees, right? And we saw from the picture that it's 30 degrees down, right? Let's go look at that. It's this right here. We did this. It's this offset right here that we're creating now. So it's 30 degrees down. So now the new number is the one they have right here. Whoops, right here. Of, whoa, is this guy right here. That's square root of 3 times 19. So you can see that's about 1.7 times 20. It's somewhere around 34. And we get that. And the angle is something above 15. This is not quite 15. That's minus 30. So 16.57 looks about good. Okay? You can get to the same point right here, noticing, in fact, it's a way to sort of double check. This is the picture of this and this load, right? Where this load is equal to Z delta, which we had up top, 8.944 at an angle of 13.43, and it was divided by 3. Okay? So we get that. Do I have that angle right? Yes, I have that angle right. So the angle stays the same, but this will be a new number, and it looks like that new number, right? This looks like it's 2.981. My, they keep a lot of decimal points handy. So now when they perform this division, remember this is the original from way up in the problem. Where am I at? This one is 100 at an angle of 10 degrees. Okay, and now if I divide the two, I just noticed as I'm doing this, I copied this number wrong. This should have been 26.57 degrees. So this was the new Z. So 2.98 into the 26.57 and 10 degrees. And lo and behold, this turns out to be the same number. So I just got to be careful that I grab the right thing. So either way, you had to go find Z originally in the first place. And nice to see that method 2 and method 1 come to the same result, 3354 at minus 16.57. And the line current here came out to the same thing, 3353, 657. Okay, so that's that. Next, we're going to move on to an open-ended problem, an unsolved problem, where we have the same arrangement, balanced Y, delta, and we're given line voltages, even though it's a Y-connected source, and a delta load. Okay, we're back with problem 12.3. And this is a Y source connected to a delta load, and we're finding phase and line currents. So we can stay straight on with this. We are given a phase voltage, right, of VAB, AB equal, VAB is 120 at minus 20 degrees. Okay, and we're given a Z, nicely there we're given a Z. So this is a line voltage already, right? And we know that IAB, so what will this be? This will be one of the phase currents, will be VAB over the Z, right? So that's 120 at an angle of minus 20 divided by 20 at an angle of 40. Okay, and that looks like 6 at minus 60 degrees for one of the phase currents. The others will now be straightforward. 6 at basically plus and minus plus and minus 120 degrees, right? So you'll have plus 60 and minus 180. All right, straightforward there. Now we need, those are the phase currents. Now we need the line currents, right? So the line currents the line currents will be IA. You can refer to pictures in your text for this. Will be IAB minus what? ICA. So what we really need to recognize here is which ones are which. Well, we have IAB. This is 6 at minus 60 degrees, right? We have that. And we need ICA, right? ICA. This one is going to be, whoops, our pointer here, come on. This one is going to be ICA is 6 at, what was it? Minus 180. Minus 180 degrees. So we want to subtract those two. Subtract the second from the first. Okay, and you can draw the, I'm sorry, this is not the one I want. 6, this is, I want 6 at 60 degrees, right? It was the farthest one out, the farthest one back around, because my IAB is at minus 60, and in a positive sequence, that next current is going to be the one back, so that's going to be at positive 60. Sorry. So we get that. And this will amount to this. We can do the math here. Actually, we could make the... we can do the picture on this as we have... Right, an easy way to do this is we've got 6 at minus 60. Whoa, back here. So that's 6. This is 60. And then we're going to subtract 6 at 60. So here's 6 at 60. 6 at 60, and we're going to take it back this way. So this will be minus 6 at 60, minus that quantity, right? So I'm taking it out. So here it is going to be down here at minus 90. So it'll be 6, the IA will be 6 times the square root of 3. We know that. And here's our angle at an angle of minus 90 degrees. So you can work this out, and that is probably the 10.392. Right? You can take 1.7 times 6 is about 6 plus 4.2 and a little bit bigger than that. So it's about a little higher than 10.2. All right, I want to move on now to the balanced delta-delta connection. All right, in the balanced delta-delta that we have here, you can see this is an easy connection. There's 3 simple loops, straightforward, easy connection to make. Okay, so like the YY, these are some obvious loops. All right, so rather than drawing all kinds of pictures, let's just make this easy. We want the 4 items, line voltages, phase voltages, line currents, and phase currents, always solving for that. First off, line voltages and phase voltages are identical. You can see that here in the picture, right, pretty clearly, right in the picture. Okay, where's my pen? Yeah, you can see that right here in the picture. There's just a simple loop. So phase voltage is across here, and line voltage is across here. So those we have. right? Nice thing here is there's no phase shift, no 30 degrees phase shift one way or the other. The phase currents now are simple Ohm's law, right? You have the voltage, the line voltage appears directly across the delta impedance. And so the three phase currents are quite easy to come by. All right, so that's 3 of the 4. The line currents, well, they turn out to be easy nodal equations. Look, what we're going for with line currents, this is the line current. We want that, and we come right over here to this node, this node. In our usual way, we've actually been doing this, and that's what we'll have. So we actually did this in the previous problem when we had y delta, and that happened because we had a balanced delta load. Same thing is true if you want the other line currents. It's just the nodal equation related to each. Okay? And the line current is related to the phase current in the usual way of the square root of 3. Okay. So let's solidify some of this with the practice problem of 12.4. We've got a positive sequence, balanced delta source supplying a balanced delta load. Right? So here we are down here. I'm just going to speed up the drawings a little and just draw 2 deltas. Right? We know there's the loads on here. And and we know, I don't know what happened with that. But here's this, and here's our sources. And the connections are straightforward. But we've got the reference in case we need them. So now we've got, if the impedance per phase of the load is 18J12. All right, so where are we at here? We're at 18 plus J12. All right, and the what we want to find is what is IA. And IA is given something, so we're given an IA right here. Right, that's the 9.6 at an angle of 35 degrees. Pick an odd one, of course. And what do we want to find? We want to find IAB. We want to find this guy here, and VAB, this here, right, given these currents and impedances. And it's balanced, so you know what's going on in every phase. Okay, so I'm just going to note, so we don't drag through the calculations, this is going to be 21.6. You can do the calculations yourself at an angle of 34 degrees. All right, and I think I'm going to do a draw. Remember, this is equal to IAB minus ICA. So I think a lot of this we'll be able to get straight off of the drawing. We also know that the magnitude of IAB is going to be I peak over I phase over the square root of 3, right? Or in this case, it's going to be I line, which is IA, right? So that's going to be equal to 5.55, something like that. Okay, so we have that much already. All we really need to get straight now is the angle. Whoops. So let's do that. Here we've got IAB is up here at, what did they give us? Well, they said IA was at 35 degrees, right? So here was a given, IA, and this is 35 degrees, right? Now we know that that is made up of two elements that are, right? This is 30 degrees. I drew it badly. This is 30 degrees, right? And this one must be IAB. I'm sorry, this one will be, this will be IAB up here, right? Because it's the positive, IAB. And this will be, I'm going to take all those up, this will be minus ICA, right? So I know if this angle is 35 and I'm 30 degrees off in my positive element to it, right? In, where am I at here? This guy is going to be positive. So that's going to be, the net angle is going to be, I'll write it all here, IAB is equal to the 5.55 at an angle of 35 plus 30, or 65 degrees, right? I should have drawn this a little more to scale. This IAB actually comes up here further, but we've made that drawing so many times we should be just fine. Now the last thing we need is VAB, and easily enough, we're good with this. VAB is what? IAB times Z delta. Okay, and that's going to be pretty straightforward. That's our 5.55 at an angle of 65 degrees times 21.6 at an angle of, where were we there? 34 degrees, right? So we should get something here that's a product, and the angle will be the sum of these, looks like 99 degrees, and 5 times 20, so it's going to be something over 110. So, you know, I'm saying it's probably 120 or something, plus or minus, I don't know. All right, so that is that practice problem. Same techniques over and over again here. It's very good. Now we're going to move on to the balanced delta Y configuration. And this is the last of the 4 configurations. So the delta Y, possibly the diciest of the 4, I don't know. But we have a couple of things we have to go after. The line voltages are already indicated. They're the same as the phase voltages. This is nice. So it's the line and phase currents that we're going to be interested in. And the first method would be to use the Kirchhoff's voltage loop law equations, do a loop. And we'll do one representative loop. Okay? And we can write the equation around this loop. It is a VAB, right, minus IA times Z delta, or ZY. Whoa, get on the right page. And then, so minus that, plus IB times ZY. Okay, and that's 0. All right, so we can pull things together and get that VAB is equal to what? ZY times IB, B plus IA. Let me write this again. VAB is equal to, taking all this stuff over to the right side, ZY times IA minus IB. Okay, but we already know that IB is the same magnitude but lags IA by 120 degrees. So that means that we can solve this easily. We can make a substitution here, the obvious one, that this is IA, the magnitude, right, times something at 0 degrees, which I'll just call 1, and then we're going to subtract something at minus 120 degrees. So let's think about that. I've got one going this way and one back here. So what are these components? Right, this one is a half, and this is the usual 0.866 thing going on. Right, square root of 3 over 2. So I've got IA times 1 minus a half. So this is going to be plus 1/2, and minus a minus 0.866. So this is going to be plus J 0.866. Right, where this is a magnitude now that we're talking about. So we can put all that stuff together. We also know that if I were to look at it over here, whoops, where's my diagram? My pointer is, if I move this negative up here, I'm going to be looking at a summing vector, which is right out there. And if that was 30, that was 30 there. Then this is, if I move them around, 180. So this is going to be my 30 here and my 30 here, correct? So this angle is going to be, VAB is going to be something at an angle of, oops, hang on a second. So this comes together as what? ZY times IA at an angle, we drew it right there, got to get the factor right, at an angle of 30 degrees. Okay, so this starts with the phase and the line voltage, and we're almost down to the line current now. So we can get IA is equal to VAB, the phase voltage, divided by Z of Y times the square root of 3 at an angle of 30 degrees. So that tells us that this current is VAB. I used capitals. I've been not good about that here. VAB divided by the square root of 3. We got that guy sort of locked in everywhere. Divided by the impedance, all at an angle now of minus 30 degrees. Okay, so that's our basic line voltage. I'm sorry, that's our basic line current, not line voltage. So we have, over here, we have the phase voltages, and the phase and the line voltages are equal. We now have, we found the line currents as individual ones. That's the phase voltage against the impedance. And here we have now found the phase, the line currents. Got to watch myself here in the Y Why am I doing that? Well, all right. Let's move on. There is another way to look at this. So you can see, oh, by the way, before we leave this slide, everything then just moves around by 120 degrees, right? So IB lags by another 120. It's down at minus what, 150, and IC lags that in a positive sequence, and IC lags that by another 120, which is minus 270 or plus 90. Okay. All right. The second method might be to transform the source. Okay, going back to the picture. We have here a delta source, right? And that's, I don't know what that was. We have here the delta source and the Y load. So if we made the delta source into a Y source, we would be back to a YY configuration that we've been to before. So here's a way to visualize that. We want to transform this delta source into something that's YY, right? We want this to turn into this, the dotted line version. And that would be, in a clean form, that would mean the whole source is changing to simply a Y. Well, that's nice. If we can do that, we then have the nice single loop equation that we had before that we like. These are very easy to work with, right? So here we have, this would be representative of the single load value. Here is that line current then, which is the same one that goes into the load, right? We can go back here to this picture. That's this up here, single one going into the load. So here we are at that line current, but now we know that the line voltage or the phase voltage, if I view it as a Y phase, I transform the phase by moving it down 30 degrees and dividing by VP. That's essentially what I've done. And oh, by the way, that's pretty similar to what happened right here when I transformed this, right? I really ended up burying the idea that here was a source transformation. Okay? And when I do that, I end up with all three of these sources transformed into the Y, and now we've converted all the analysis into a YY analysis, and we'll be back to the same thing. So no surprise that when I went back a slide and did the delta Y without the source transformation, I was actually hidden in that math. It's the only math there is, but hidden in the math was basically a source transformation. Here I just made it obvious, okay? So after the transformation, I'm sort of left wondering, this was my own thought, was this a single Y or a single delta? What did I really do here? I ended up with a single loop. So however you want to view it, it's a Y because we made a delta to Y transformation in the source, but it just made things very simple. An example of that last transformation takes place in your text in example 12.5. Here we begin by just calculating the Y. What is the load? So we put it in phasor form, right? Some length at a positive angle. The source voltage is this. So this was a line voltage, right, out of a delta for a delta source. And when the delta is connected, is transformed, right? We just did that. Here is that simple transformation. This is not a bad way to approach this, so I think about remembering that. And then you have a simple, the simple equation here, right? And it's just follow through the math at that point. So that's a good thing to be doing. All right, practice problem 12.5. Let's do this one with maybe a little more math to it. All right, so we got a balanced delta Y circuit here. What I'm going to do is say I'm going to go for the single loop equivalent, right? And remember, this is what we're after up here. And if this voltage, we are given a line voltage in a delta configuration. But in a Y configuration, this voltage, VAN, would be VAB, right, over the square root of 3 at an angle of minus 30. We did all those derivations. But remember now, this is actually a phase shift because it was calculated assuming a 0 degree up here. So we're really looking then at 240 at 15 degrees divided by the square root of 3 and shifted minus 30 degrees. So we end up with a number now of 240 over the square root of 3. I don't think I need to calculate that yet. At minus 15 degrees. So that is our phase voltage. So then IA, since we have a Y load, we were given ZY. So IA is now VAN over ZY, right? And we're given ZY. We'll have to crank that one out. That's not a nice 345 or anything like that. So we'll stay with it. We've got our 240 over the square root of 3 at an angle of minus 15 degrees. And we're going to divide that by ZY. So let's take a minute over here for ZY is equal to 12 plus J15. And I'm going to say that's equal to, I sort of calculated it, but not too close. It's 19.2. We know it's a little bigger than 15. That's almost an equilateral triangle, not quite. So I'm expecting this to be somewhere in the neighborhood of 45 or 50 degrees. And I think it turns out to be 57.3, right? Maybe some change, I don't know. So that's going to come over here and divide this by 19.2 at an angle of 57.3 degrees. And so what does that give us when we do all the cranking around? We end up with something here. We can get the angle. That may give us a clue. This is going to be minus, so 15 looks like I'm sorry, this is 51. I knew it was closer to 45, 51 degrees. So 51 brought up to the top is going to be minus 66.3 degrees. And all of this math, you'll just have to trust me on it. It's about 7.22 by the time you grind all that out. Actually, I could guess if this is 240 and this is 20, that means it's 12 divided by the square root of 3, which is about 1.7. So 7, this makes sense. This is one of our currents. And the other 3, oh, that turns out to be the first one down here. That turns out to be this one down here. and the other 3 are just shifted by the 120 degrees, the other 2. Okay? So there's that. Here, by the way, I just posted it. You have this in your book for a great reference. I simply wanted to point a couple of things out. It's a handy table, maybe for orientation as much as anything. But remember when we did the YY configuration here, everything worked out really nice. The phase voltages and turned easily into, we just got done using a variation of these, into line voltages, shifted 30 degrees multiplied by square root of 3. Phase line currents turned out to be the same as phase currents, or vice versa. Phase currents turned out to be the same as line currents, okay? And some of those nice parallels, like in the delta Y that we just finished, some of those nice parallels occur again, like down here with this. Here we are again with that, and here we are again. The worst one, it turns out, where everything was unique, turns out to be this guy over here, the Y delta. But everything was calculated, so we always had those to work with. Just a handy piece to kind of keep as a reference point. I use it a little bit, maybe to see if I've made some gross error, because it's kind of an orientation device, I would have to say. All right, we're going to move now to power in a balanced system, and I'll cover as much as I can here, and there may be a separate part where we just work problems. But I'd like to talk a little bit now about power in the balanced system. The important thing here is power is a time domain entity. And so we're going to be discussing that with these phase voltages. And notice they are a function. The square root of 2 reminds us what? These are RMS values. So a peak value, square root of 2 RMS value, and now the time function. And so here are all 3 of the time functions for the voltages involved. Okay? And we're doing this in a Y connect. You can see that just by the subscripts on the names. Okay. Now, the current is, we've done these calculations. We're just generalizing them now with a phi. We're saying the current is, the RMS value is the square root of 2 times the peak current value. And now we're going to allow for an offset, right? This is a line current, is the phase current in the Y system. And it turns out this will be independent of the Y or delta configuration. But we've added now a phase shift. And it's the phase shift. The current is not in phase with the voltage. That's what's being referred to here. And so we have the next phase shift. IB corresponds to VBN. So there's that reference, minus 120. And here's the other one for IC. All right, so those are the values of the current and voltage that we'll be working with. Now the power, the total power in the system, is the sum of the 3 individual powers, which are what? Simply the product of the respective terms here. The product of what have we got? This, whoops, the product of this voltage with that current, and vice versa. This voltage with that current, and that voltage with that current. Okay, that's all we're indicating here at this point. Time domain. So you can imagine in the time domain, things are going to keep hanging on and hanging on. You're just going to be dragging a lot of terms around, so it could get painful. Expect trig substitutions. That's what I'm saying. But we know, because we've done some of this, we now have the product is what? The square root of 2 times the square root of 2. So we get our 2 right here to begin with. 2 VP IP, straightforward, times the cosine of omega t minus. So I'm only showing you right now the first term, VAN times IA, right? It's that square root. Now I'm going to add the second term, and of course I've factored it out because it's not needed to repeat all that 2VPIP. So here's then the product of the second two terms, the ones way over here, off up here on the right. Okay, and then finally the third three terms. And we close the bracket down here on the right. Okay, so all of that looks super good. Until now, we have to make something out of this. We have this omega, we've got theta, and then we've got a bunch of fixed phase shifts. So we now get down to something like this from the text. I just copied this, obviously. There's our VP IP, and something happened now that we've got this 3 cosine theta, and somehow we got 4 terms, and they're all single cosines instead of all these products of cosines. So what happened here? How did we get lucky or not with this, right? Well, we have to remember, of course, it's trig function time, that cosine of omega t times cosine of omega t plus theta. Aha! Remember what this is? We could look it up. It's the nasty thing of 1/2 times cosine 2 omega t minus theta cosine theta plus cosine theta plus cosine 2, this is a theta, omega t, let's see, 2 omega t, I got to be careful here. So it's the cosine 2 omega t, I got to do this plus theta, and then cosine of omega t minus omega t minus omega t minus theta. So that would be cosine of minus theta, which is the same as the cosine of plus theta. So that's going to reduce, right, to just that little bit right there. I'm going to do that substitution. Only now we're going to have to do that on all of these parts over here. I took them away. And so what happens is you get this. Here's the 1/2. That's going to come out of every term. So that got rid of our 2 out front, leaving us with just this. Every one of these 3 terms over here, right, 1, 2, 3, is going to contribute a cosine theta. So there's 3 of those. And then here's cosine 2 omega t minus theta. What did I have? Oh, I got this wrong from the beginning. This was a minus in here, right? So that was that made the plus cosine right away. So then that was 2 cosine 2 omega t minus theta, where I added those 2. And then I did to the next term, I had the same thing, where I had to add omega t minus 120 degrees with omega t minus theta minus 120 degrees. Right, so that gave me 2 omega t minus theta minus 240 degrees. Then I do it again with plus 120, and I get plus 240 degrees. So messy as it is, that's where all those terms came from. That whole thing reduced to those 3. And we can just keep doing math on that. This, by the way, as we get, I would take some time to convince yourself of this, because when we get into frequency response, we're going to be seeing this more and more. we make the substitution 2 omega t minus theta, because that's going to that occurs a bunch, right? It occurs here, it occurs here, it occurs here. So it allows us to simplify this to be something like this, just a cosine alpha. Okay, and then here's a sine alpha. Now this became crazy because of what? I needed to expand cosine. This is going to be cosine alpha minus 240, right? So I had to go in and make yet another substitution, and that substitution is this one. I'm going to have to make it again down here with cosine alpha plus 240. So the substitution is cosine of alpha, and I'll put it as plus and minus, in our case 240, right, is equal to cosine alpha cosine 240 plus or minus sine alpha sine of 240. Okay, a little crowded there, but that's a substitution that got made in all of this to now get to the final one, which I've written over quite a bit of, which is VPIP. There's our 3 cosine coming down. There's our cosine alpha. And now here's all this. Let's see, maybe I can erase some of my stuff. I could finally use this, perhaps. Well, now when I need it, I can't make it happen. All right, if I could erase that, you would see 3 VPIP. You can follow this in your text. Is equal to 3 VPIP. Because all of this resulted from what? I'm going to lose a lot because I have the sine of 240 and cosine of 240. Those are going to be fixed numbers, right? So I'm going to gain some and lose some in there, and you really have to just follow all that math through. I'm not going to do it here, but a whole lot of this collapses to be 2 times minus 1/2 cosine of alpha, where alpha is the 2 omega minus theta. Okay, since I kind of overwrote things there, it's important at least to write that final result of all that, which was 3 VPIP cosine of theta. Okay, and remember this was what? This is the power in the load. Now, this is actually quite a surprising result because we have a sinusoidal system, and we calculated in all of this, we calculated the instantaneous power. And yet when we do all the trig substitutions and all the reductions and cancelings, we come down to this, and isn't this remarkable? This is a constant. Okay? I think that's pretty amazing. It's a constant. And it's a constant as a function of the peak values and this theta, right? Theta is the result of a load, right? So everything is influenced, the source and the load, and you end up with a constant instantaneous power. This is very nice from a power company point of view. Okay, so this was the real power, the power delivered. And what I want to do is just briefly talk here, just kind of make a diagram so you can see. I think you probably know where this stuff is, but let's just be assured. We calculated P. What did we actually calculate? We calculated this. If we take the phase, we calculated the real power, right? That's what happened with this cosine of p, right? If we have reactive power, right? So this is the thing called P. The reactive power is Q, right? The sum of these, right? Aim for that point, is S, right? This is the apparent power. This is reactive, of course. That's the real power. And these sum. And where's the angle? This is the angle, right? So you can see if the load and the whole delivery system was all in phase, all of this apparent power would really be folded down here, and it would all be real power delivered to the load. So it's the load that takes the apparent power, which remember is just the apparent power is, this is the VP IP. It's the big guy, right? It's all that could be. This is the power per phase, by the way. This that I listed as total power. My drawing here is per phase. VP IP per phase. Okay, this is going on per phase. So there is that. All right, so this was our total power. Up here, it's constant, right? And now we're going to look at these portions, right? So the part we're interested in, the real power, quite naturally, is our VP IP times the cosine of theta, function of the load. And the reactive power, likewise, is VP, or similarly, times the sine of the angle. All right? And the apparent power, I've indicated, this again is per phase. And so the complex power, I'm just going to write it. He indicates it with a bold. Then is simply P plus JQ. And it's sometimes indicated as something that looks like apparent, but it's just the bold S. Okay? And this is going to be the voltage times the current, but if these are phase related, it's got to be conjugate math. Okay, so remember to do that. And then so the total power, or the total average power in all three phases is simply the sum of these individual powers. So that's the power total will be 3 times the power per phase. Oops, that's a total, right? And you can quickly do the math here. We're right back to where we were up top. 3 times the V phase, I phase, cosine theta. But we also know these in terms of line voltages, right? So square root of 3 times the line voltage and the line current, also cosine theta. This is in your book. One of the reasons we're able to do this goes back to this amazing thing up top that you have, even though it's time varying, you end up with a constant. Quite remarkable. quite remarkable. And but it contains all the influences, all the elements of the circuit itself. The phase angle from the load, and any interaction. Then, I mean, the load is what causes the phase angle to differ in the from the source. Right? It causes the phase shift between the current and the voltage, line current, line voltage, phase current, and phase voltage. All right, he nicely sums up in the text this fact that the total complex power is 3 times the complex phase power. There's our phase arithmetic again, our conjugate arithmetic, and you can put that in any place that you want, right? And here it is broken out in terms of the P's and Q's. All right, I'd like to close this lecture with just a quick look at practice problem 12.6. You have an example problem there in the text, that's 12.6, that's quite thoroughly worked out. We don't have time for that, but I will do this, where we take the results from a previous problem that we worked, 12.2, and calculate complex power at the source and the load. So that had a Z of the Y, which was 24 plus J19. And I'm just going to tell you this is 30.6 at 38.4. Okay, and the power to the load. Now remember, we're looking at, we can look at apparent power, and we'll look at and then we'll break that up into real power, complex power with that, right? So the apparent power will be to the total load 3 times VP IP. All right, VP we had that from back in that problem, or we can take the V of the phase. This could actually be simply 3 times IP times Z times another IP, right? And if I do all that, I get 3 times, and it was 3.75 was the IP, was 3.75 at an angle of minus 866 for one of the phases. All right, so 3 times 3.75 times the Z, this is 30.6, times another 3.75. And this comes out to 1291. Okay, so now we can break that up into our P's and Q's. The P would be 1291 times cosine, right? Cosine of 38.4 degrees. And Q should be, we'll leave an equal for that. Q will be 1291 times the sine of 38.4 degrees. Now we know Q is going to be the sine of a small number is going to be less than the cosine of that small number. So Q is going to come out less than P to be sure. And those values are here, 10, 12, whoops, or thereabouts. And this is some in the 800s, 801 or 802, somewhere in there. Okay, so our load power, our complex power at the load, is 1012 plus J802. Okay, we can say that's the load. Now if we want to look at the source, the power at the source, and it's going to have a minus sign because it's delivering power. Okay, so the source power is going to be, I'll put the load up here, is going to be 3 times VP IP, but this has to be conjugate math now, right? Because it doesn't know, it's not just burning up the current, it's not converting the current to voltage, and then that product becomes viable power. The load has moved the current from the phase that was generated. So this is now going to be equal to 3 times, we're going to have to keep everything with the phase source back in that one, whoops, was 120 at an angle of 30 degrees, right? And then it's times 3.75, but the conjugate, instead of minus 866, is going to be at an angle of plus 866. And all of this is going to give me 1350 at an angle of, add these two, 38.66 degrees. Okay? And if I break that up into pieces, I'm going to have about 1054 plus J 843. Okay? And because it's delivering power, it will be minus, right? Because, and that's a notational thing, right? Here we are. We've got plus voltage, and we've got current coming out, right? Current coming out. So that product, unlike the product at the load where you've got also plus voltage, but you've got current coming in, right? So this product, this power is positive, and this power is negative. Okay? And those are the answers. I obviously checked them before I did it, but all right, so that concludes this lesson. It almost seems like there needs to be a lot of work working power problems, and so we'll need to address that.